So again, the reason for covalent bonding is electron sharing will occur only for that noble gas configuration to get a filled outer energy level. That's why it happens. Now let's look at covalent bonds, single bonds. So it's when two atoms will share a pair. So we have two hydrogen, and now they share. Hydrogen again just wants to be like helium. Fluorine has 7 each. They both want 8, and they come to an agreement. They both have the same electronegativity. They can't rip it apart like fluorine and hydrogen or fluorine and sodium. Fluorine will just bully that in sodium or any of that alkali or anything except a fellow non-metal, and it will take that electrons. But here, they're both equal in electronegativity because it's the same element. They share. There we go. They're happy. And here we have carbon dioxide molecule. So this is a double bond, which we'll get to in a second. Carbon tetrafluoride. Carbon wants 4. So down here, carbon wants 4. Fluorine just wants 1, and they come to an agreement. They will share. Fluorine has 8. Carbon has 8. And we can draw these structurally like that. Excuse me, not an H. It's an H. Okay, F2 is like that. CO2, we'll get to that double bonds in a bit. Carbon tetrafluoride. You can draw the structural. If you wish, you can draw the other valence electrons in these that are not bonded. Okay. Double covalent bonds, they share 2 pairs, 4 total electrons. So here we have 2 oxygen atoms up here, and they share. Oxygen, recall, has 6 valence electrons. It wants 2. Oxygen says, hey, I want 2, I have 6. This oxygen says, hey, I have 6, I want 2 more. Well, let's just give each other 2, share with each other, and we'll be happy with 8. And they are. So this on the left has 8, and on the right has 8, and they're sharing. Another way we can look at it with X's and O's, so you can draw X's if you want for your electrons. This one has 8 on the right, and the one on the left has 8. So they share. And we can draw that structurally with a double bond. Each line represents a pair. Here's carbon dioxide on the bottom here. Double bonds. They both share 8. 1, 2, 3, 4, 5, 6, 7, 8. They give 2 each on each side. So this carbon needs 4. Each of these oxygen, so this one needs 4. The oxygens each need 2. The carbon really makes out. He had 4, now he has 8. So we have triple covalent bonds. Atoms will share 3 pairs of electrons. Notice the nitrogen here. They share a total of 3 pairs, or 6 total of electrons. They each give 3. Nitrogen had 5 valence electrons. They want 3, so hey, what better way to get to that noble gas configuration of 8 than to share? And here at the bottom we have hydrogen cyanide. That's the poisonous gas. We have carbon. This is an interesting one here. Carbon wants a total of 4. Now it gets 3 from nitrogen and 1 from hydrogen. Carbon gives 1 to hydrogen. Carbon gives 3 to, or really I should say shares 3 with nitrogen. And then the structural formula here, 1 single bond and 3 bonds there, that's a triple bond. And we see the unbonded valence electrons here. Coordinate covalent bond is where one atom will contribute both bonding electrons. They're such good guys, such nice guys, that they don't have to take anything in return. So look here at sulfur dioxide. Sulfur here has 1, 2, 3, 4, 5, 6, 7, 8. It already has a filled valence electron energy level. Oxygen comes over. He wants 2 really bad. Look at that, free. This sulfur is not using it, so out of the goodness of its heart, it says, go ahead. You can take that electron. Just stay close. I'm not going to give it to you, but you can use it. So over here, it's called a coordinate covalent bond. If we do the structural formula here, we have a double bond with that oxygen here, and the oxygen here. Now, often you'll see it represented as an arrow going to the oxygen here, because that means that the sulfur gave the oxygen, or the electrons, didn't give it, but it's letting it engage in a coordinate covalent bond. Oftentimes you'll see that, or you won't, with the arrow. So just be aware, if you see an arrow like that, that means it's a coordinate covalent bond. This is a brief tutorial that I found online. Now we are going to be drawing Lewis dot structures, and this is a brief tutorial I did find online. It's basically just a step-by-step process. Usually, though, it's not as cut and dry as just following the numbers. You kind of have to work with it, and just takes practice and experience, really. Some people get it right off, others it might just take more and more practice. So this is for a neutral molecule, carbon dioxide, for example. So you have to decide how many valence electrons each element possesses. And that's what a Lewis dot structure is anyway. It's showing the valence electron. Now carbon has 4 valence electrons. Oxygen has 6. If there's more than one type of atom in the molecule, put the most metallic or least electronegativity negative in the center. So that would be carbon. So here we have carbon. It's the least electronegative, and it's more metallic than oxygen because it's more to the left. So now we're going to arrange the electrons so each atom contributes 1 electron to a single bond between each of them. So here we've arranged it so they each contribute 1 single bond. Now we count the electrons in each atom. Do they have 8? Are the octets complete? If so, hey, great. But we look here, it's not the case. Oxygen has 7, carbon has 6. Not complete. Carbon needs 2 more, oxygen just needs 1 more. So that should kind of raise a flag, well, maybe double bond. So if the octets are incomplete, add more electrons to be shared. Move 1 electron per bond to make another bond. Okay, so note that in some structures there will be open octets, or atoms that will have 10 electrons. So we'll get to that later. You don't always have 8 electrons. What we're going to do here, they move 1 electron, so that's what our rule is, just try 1 more electron from each to make a double bond. So the oxygen gives another one, and the carbon will give another one. So then you count in 4 or 5, we count 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy. And this oxygen is happy. 1, 2, 3, 4, 5, 6, 7, 8. So they all have 8. Again, repeat 4 and 5 until all octets are full. We might have to add a triple bond. Now we want to redraw the dots so that the electrons on any given atom are in pairs wherever possible. And so we redrew it, and now we have our pairs. So in retrospect, what you want to do is put the least electronegatives in the center, or the most metallic in the center. then put their valence electrons around it, and then start playing with it to see which ones could give what to get a full octet. Again, it does take practice. Some of these electron dots are pretty easy. Some are bare. Some you can just spend a long time on, and they just are really tough. But you just gotta keep practicing it. Polyatomic ions, which we'll get to in more detail next chapter, we'll be naming these and everything. They're a tightly bound group of atoms that has a positive or negative charge. So these are a group that all of them have a negative charge of 3-. Every one of it. Not individually. That doesn't mean O has 3-, this O has a 3-, or P has a 3-. Just as a group, they all have 3-. 3 electrons came in there, and it allowed them to all bond together as a group. So this is kind of like, these guys, the polyatomic ions, are kind of like a clique. They're just a whole group of girls or whatever that just are tightly bonded, and together they're a group. And they go around and they'll bond maybe with one element, or with 2 other elements, or with even another element. Okay, so each of these polyatomics will now have the capability as a group to bond with something else. It's a unit. Talk a little bit about bond dissociation energy. This is the energy required to break the bond between 2 covalently bonded atoms. So if we have H here, the energy that requires to break that bond is a bond dissociation energy. Now some will have higher bond dissociation energies, like fluorine, F2. This is a higher energy than H2. Resonance is where a molecule or polyatomic ion can be shown in 2 or more ways. For example, we have a molecule here. This is a polyatomic ion. But we can draw it, like in the first case, with a triple bond and then a single bond here. And notice where the electrons are. Or we can draw it with 2 double bonds and notice where the electrons are. Or we can draw it with a triple bond connected to the carbon and the sulfur. So that's resonance. That's where you can make a molecule in more than one way. So this molecule will exist as 3 different formulas or structures, as will this. So we can do it with this double bond here or double bond here, and the negative here or the negative here. Resonance, you can draw it in more than one way. The classical example of resonance is benzene here, and we have a ring. So we can have the double bonds between the carbons here, here, and here, or we can do it here, here, and here. There are exceptions to the octet rule, and that's when molecules have an odd number of valence electrons, like 7, or they could have a fewer or more than a complete valence octet. So for instance, if we look at phosphorus pentafluoride, look at the number of electrons that phosphorus has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Phosphorus would be using 3s, 3p, but available to it would be a 3d orbital. So there are exceptions to the octet rule.